Welcome. Thank you for joining us here at the Z-Files, where we will start now by asking you to imagine a future where the most precious materials we need are not clawed from the earth beneath our feet, but quietly harvested from rocks drifting through the void of outer space. Asteroids, those ancient remnants of our solar system's birth, may hold resources of unimaginable worth, waiting in silence for us to reach them. The economics of asteroid mining blend staggering possibilities with enormous challenges, a careful balance of risk and reward that could reshape industry, geopolitics, and our relationship with space itself. Let's explore this quietly revolutionary idea together. Part 1. The value hiding in the dark. To understand why anyone would consider mining asteroids, we need to start with what they contain. Asteroids are leftover building blocks from the formation of our solar system, fragments that never coalesced into planets. Many are rich in metals that are rare or difficult to access on Earth. Platinum group metals, including platinum, palladium, and rhodium, are particularly abundant in certain types of asteroids. These metals are essential for catalytic converters, electronics, and various industrial processes. On Earth, they're expensive and hard to extract. In space, they may exist in concentrations far higher than any terrestrial mine. Consider a single metallic asteroid, perhaps a kilometer across. Such an object might contain more platinum than has ever been mined in human history. One frequently cited example is the asteroid known as 16 Psyche, a metal-rich body in the main belt between Mars and Jupiter. Some estimates have valued its metal content in the quadrillions of dollars, though such figures are highly speculative and assume we could somehow bring all that material to market without crashing prices. Still, even a fraction of that value would be transformative. Beyond precious metals, asteroids offer something perhaps more immediately practical for space exploration: water. Many asteroids, particularly those classified as carbonaceous chondrites, contain significant amounts of water locked in minerals or existing as ice. Water in space is extraordinarily valuable, not for drinking alone, but because it can be split into hydrogen and oxygen. Hydrogen and oxygen make rocket fuel. If we could refuel spacecraft in orbit or beyond, using water mined from asteroids, we would eliminate the need to transport all our propellant from Earth's deep gravity well. This could reduce the cost of deep space missions dramatically. Rare earth elements present another category of interest. These 17 metallic elements are critical for modern technology, from smartphone screens to wind turbines to military equipment. China currently dominates the rare earth market on Earth, controlling most of the supply chain. Asteroids likely contain rare earths in economically interesting concentrations, and accessing them could shift geopolitical balances. Of course, this assumes we can extract and return these materials at a cost lower than terrestrial mining, a question that remains very much open. The challenge with valuing asteroid resources is that we're speculating about future markets. If someone brought back 10,000 tons of platinum tomorrow, the price of platinum would plummet. The market can only absorb so much supply before values collapse. This means the true economic potential of asteroid mining isn't just about the raw tonnage of valuable materials, but about how carefully and gradually those materials are introduced to the economy. Some models suggest starting with the highest value, lowest mass materials first, shipping back small quantities of platinum group metals while leaving the bulk iron and nickel for in-space construction. Others propose focusing entirely on water and volatiles for the burgeoning space economy, never returning material to Earth at all. There's also the question of which asteroids to target. Near-Earth asteroids, those whose orbits bring them relatively close to our planet, are the most accessible. Reaching them requires less fuel and time than traveling to the main asteroid belt. Scientists have identified thousands of near-Earth asteroids, and missions like OSIRIS-RX and Hayabusa-2 have demonstrated that we can reach them, study them, and even return samples. Not all near-Earth asteroids are equally valuable, though. Some are rubble piles, loose collections of rock and dust held together weakly by gravity. Others are solid metallic bodies. Identifying which asteroids are worth the investment requires detailed remote observation and, eventually, prospecting missions. The dream, then, is this: identify a resource-rich asteroid, send robotic spacecraft to extract materials, and either return those materials to Earth or use them in space to build infrastructure, refuel missions, or manufacture components. The economics hinge on whether the value of what we extract exceeds the enormous cost of getting there, setting up operations, and bringing anything back. Right now, those costs are prohibitively high. But technology is advancing, launch costs are falling, and the value of space-based resources may rise as humanity's presence in space grows. Whether asteroid mining becomes reality depends on navigating these uncertainties with care and patience. Let's turn now to the question of cost, the formidable barrier that stands between ambition and achievement. Part 2: The price of reaching out. The economics of asteroid mining begin with a simple, daunting fact: space is expensive. Launching anything from Earth's surface into orbit requires overcoming our planet's gravity, which demands enormous amounts of energy. For decades, launch costs hovered around $10,000 per kilogram, making even small payloads prohibitively expensive for all but the most essential missions. Recently, reusable rocket technology has begun to change that equation. SpaceX's Falcon 9, for instance, has brought costs down to roughly $2,500 per kilogram to low Earth orbit, and the company's Starship aims to reduce that further, potentially to a few $100s per kilogram if fully successful and rapidly reusable. Even so, launching the equipment needed for asteroid mining, including spacecraft, extraction tools, processing equipment, and propellant, would require dozens or hundreds of launches. The capital expenditure, or CAPEX, for a first asteroid mining mission could easily reach into the billions of dollars. Once in space, the spacecraft must travel to the target asteroid. This journey requires propellant for maneuvering, and the amount needed depends on the asteroid's orbit. The term delta V, short for change in velocity, measures how much speed a spacecraft must gain or lose to reach its destination. Near-Earth asteroids vary widely in their delta V requirements. Some are easier to reach than the Moon, requiring less fuel to rendezvous within a lunar landing mission. Others demand far more, approaching the difficulty of traveling to Mars. Selecting the right target is crucial, balancing resource value against accessibility. Engineers must also account for the return journey if materials are to be brought back to Earth, which adds further delta V requirements and propellant mass. Propellant itself is heavy, and carrying it from Earth is inefficient. This is where the concept of in-situ resource utilization, or ISRU, becomes compelling. If a spacecraft could refuel at the asteroid, using water or other volatiles extracted from the body itself, it could carry less propellant from Earth and extend its operational life. Some mission concepts envision sending a small robotic prospector first, which would confirm the asteroid's composition and even begin extracting water to produce fuel for a larger follow-up mission. This staged approach reduces risk and spreads costs over time, but it also delays returns and adds complexity. The extraction process itself presents technical and economic challenges. For a metallic asteroid, mining might involve drilling, blasting, or even using focused sunlight to melt and separate materials. For a carbonaceous asteroid rich in water and organics, heating the surface to release volatiles might suffice. Each method requires specialized equipment that must function autonomously in microgravity, exposed to temperature extremes and radiation, with no possibility of hands-on repairs for years. Developing and testing such equipment on Earth, and then qualifying it for space, is expensive and time-consuming. Robotic systems must be extraordinarily reliable, because a single failure could render the entire mission a loss. Processing the extracted material adds another layer of cost. Raw asteroid material isn't immediately useful. Metals must be refined, water must be purified and electrolyzed, and any other valuable elements must be separated and concentrated. Doing this in space, far from Earth's industrial infrastructure, requires compact, efficient systems that can operate with minimal power and maintenance. Some concepts propose doing only minimal processing at the asteroid, returning raw material to Earth or to a processing facility in lunar orbit. Others suggest building complete refineries in space, which would increase upfront costs but could serve multiple missions over time. Then there's the question of returning the product to market. If the goal is to supply Earth with platinum or rare earths, the refined material must be transported back, likely in small, dense payloads that can survive re-entry or be retrieved in orbit. If the goal is to supply the space economy, the material might never come to Earth at all, instead being delivered to orbital depots, lunar bases, or deep space missions. The latter scenario is attractive because it avoids the cost and complexity of re-entry, but it depends on a robust space economy existing to buy the products, something that remains largely hypothetical for now. Operating costs, or OPEX, include mission control, data analysis, ongoing spacecraft maintenance, and the costs of any follow-up missions to repair or upgrade equipment. These costs accumulate over years or even decades, since asteroid mining missions would unfold over long timescales. A single mission might take 5 years just to reach the asteroid, then operate for several more years extracting and processing material. Investors would need patience and deep pockets, waiting years for any return while capital sits locked in expensive, distant hardware. Financial models for asteroid mining often include break-even analyses, attempting to determine how much material must be returned, at what purity and market price, to recoup the initial investment. These models are sensitive to assumptions. A small change in launch costs, extraction efficiency, or market price can swing a mission from profitable to ruinous. Most credible analyses suggest that the first missions will operate at a loss, serving as technology demonstrations and data-gathering exercises. Profitability, if it comes, will emerge only after multiple missions have refined techniques, reduced costs, and established supply chains. The timeline for reaching profitability is uncertain, with estimates ranging from the late 2030s to the 2050s, depending on how quickly technology advances and how much capital is willing to flow into the sector. Part 3. The machinery of extraction. The technology required to mine an asteroid doesn't exist yet, not in any proven, flight-ready form. What we have instead are concepts, prototypes, and lessons drawn from terrestrial mining, space exploration, and robotics. Bringing these together into a working system represents an engineering challenge of remarkable scope. Each component must function in an environment utterly unlike anything on Earth: near-zero gravity, extreme temperature swings, vacuum, and radiation, all while operating autonomously millions of kilometers from any human oversight. Propulsion systems come first. To reach an asteroid and maneuver around it, spacecraft need efficient engines. Chemical rockets, the workhorses of current space travel, are powerful but consume propellant quickly. For long-duration missions to asteroids, ion drives or other electric propulsion systems offer better efficiency. These engines accelerate ions to high speeds, producing gentle but continuous thrust. NASA's Dawn mission used ion propulsion to visit the asteroids Vesta and Ceres, demonstrating that such systems can handle deep space travel. However, ion drives require substantial electrical power, typically from solar panels, and they're slow to build up speed. A mining mission might combine chemical rockets for initial departure and major maneuvers with ion drives for the long cruise and fine adjustments near the target. Once at the asteroid, the spacecraft must rendezvous and match its orbit. Asteroids rotate, sometimes tumbling unpredictably. Their surfaces are irregular, covered in boulders, dust, and perhaps loose regolith. Landing on such a body isn't like landing on a planet. Gravity is so weak that a spacecraft could bounce off if it approached too quickly. Some mission designs avoid landing altogether, instead using harpoons, anchors, or nets to secure the spacecraft to the surface. Others propose hovering just above the surface, using thrusters to maintain position while robotic arms reach down to scoop or drill. Japan's Hayabusa 2 mission successfully collected samples from the asteroid Ryugu by briefly touching down, firing a projectile into the surface to kick up debris, and catching some of it in a collector. Scaling this up to industrial quantities would require more robust systems, but the principle holds. Extraction methods depend on the asteroid's composition. For a rubble pile asteroid, simply scooping up loose material might suffice. A robotic arm with a bag or container could gather regolith, much like a bucket on a construction excavator. For a more solid body, drilling becomes necessary. Drills designed for asteroids must work without the benefit of gravity to provide downward force. Instead, they might use rotating screws or anchors to pull themselves into the rock while the drill bit grinds away material. The drill must also handle unknowns. Is the rock hard or soft, brittle or ductile, uniform or layered? Autonomous systems would need sensors and adaptive algorithms to adjust technique in real time. Heating represents another extraction approach, particularly for asteroids rich in water or volatiles. Enclosing a patch of surface in a tent or dome, then heating it with electric elements or focused sunlight, could release water vapor and other gases. These would be captured, condensed, and stored. This method, sometimes called volatile extraction or baking, requires less mechanical complexity than drilling but demands careful thermal management and efficient collection systems. Water extracted this way could be electrolyzed into hydrogen and oxygen for propellant, or stored as is for life support in future crewed missions. Processing extracted material on site poses its own challenges. Refining metals in microgravity is difficult because many separation techniques rely on density differences and settling, processes that require gravity. Alternative methods include magnetic separation for certain metals, electrolysis in molten salt baths, or even centrifuges to create artificial gravity. Each approach requires energy, and energy in space is precious. Solar panels are the most common power source, but they're less efficient far from the sun, and asteroids in the main belt receive only a fraction of the sunlight that Earth does. Nuclear power sources, such as radioisotope thermoelectric generators or small fission reactors, could provide steady power regardless of distance, but they add mass, cost, and regulatory complexity. Storage and transport mechanisms must be designed for the long haul. Refined metals might be cast into ingots or formed into simple shapes for easier handling. Water and volatiles would be stored in insulated tanks, kept cold to prevent boil-off. If the plan involves returning material to Earth, the spacecraft needs a cargo module capable of surviving reentry. For precious metals, this might be a small, dense capsule that descends like a meteorite, slowing with a heat shield and parachute. For larger quantities, multiple return trips or a series of smaller payloads might be necessary. Communication and control add another layer of difficulty. Radio signals between an asteroid and Earth can take minutes to hours, depending on distance. This delay makes real-time remote control impossible. Instead, mining spacecraft must operate with high autonomy, making decisions based on pre-programmed instructions and onboard artificial intelligence. If a drill bit breaks or a collector jams, the system must diagnose the problem and attempt a fix without waiting for instructions from Earth. This requires sophisticated software, extensive testing, and redundancy in critical systems. Engineers must anticipate as many failure modes as possible and design workarounds, knowing that some problems will be entirely unexpected. Radiation is a silent threat. Beyond Earth's protective magnetic field, spacecraft are exposed to cosmic rays and solar radiation. Over months or years, this can degrade electronics, solar panels, and materials. Shielding adds mass, so designers must balance protection against weight. Some components might be buried within the spacecraft structure, using other equipment or propellant tanks as makeshift shielding. Radiation-hardened electronics, developed for military and space applications, are more resistant but also more expensive and sometimes less capable than commercial equivalents. The technological roadmap for asteroid mining involves incremental steps. Early missions might focus on reconnaissance, mapping asteroids in detail and measuring their composition with spectrometers and other instruments. Follow-up missions could test extraction techniques on a small scale, perhaps gathering a few kilograms of material. Only after proving these methods would full-scale mining commence. Each step reduces risk and provides data to refine subsequent missions. Companies and space agencies pursuing asteroid mining understand that this is a long game, requiring patience, investment, and a willingness to learn from setbacks. The machinery of extraction is still being imagined, prototyped, and tested, a slow assembly of capabilities that may one day turn distant rocks into industrial resources. With the technology sketched out, we can consider the broader infrastructure that would support these ventures. Part 4. Building the roads to riches. Asteroid mining cannot happen in isolation. It requires an infrastructure, a network of capabilities and facilities that extend from Earth into deep space. Think of it as building roads before sending trucks. Without launch facilities, tracking stations, refueling depots, and processing hubs, even the most advanced mining spacecraft would struggle to operate efficiently. Developing this infrastructure is itself a massive economic undertaking, one that governments, private companies, and international collaborations must somehow coordinate and fund. Launch infrastructure is the foundation. Every kilogram sent to an asteroid must first escape Earth's gravity. This means rockets, launch pads, fuel production facilities, and ground support teams. As mentioned earlier, reusable rockets have begun to lower costs, but demand for launches is rising across many sectors. Satellite constellations, crewed missions, space stations, lunar exploration. Asteroid mining would compete for launch capacity, and any surge in demand could drive prices back up unless manufacturing scales to match. Some concepts propose building dedicated heavy-lift vehicles optimized for deep space cargo, capable of lofting large mining rigs or propellant tanks in single launches. Others suggest assembling spacecraft in orbit, launching components separately and docking them together, which allows for larger and more complex systems than any single rocket could carry. In-orbit infrastructure could include refueling depots, stations where spacecraft top up their tanks before heading to asteroids. These depots would stock hydrogen, oxygen, and perhaps other propellants, supplied either from Earth or, eventually, from lunar or asteroid sources. A spacecraft departing Earth with empty tanks and refueling in orbit would be lighter at launch, reducing costs. It could then take on a full load of propellant for the journey ahead. This concept, known as orbital refueling or propellant depots, has been discussed for decades and is slowly gaining traction as companies and agencies plan missions beyond low Earth orbit. Establishing even one functioning depot would be a major milestone, proving the concept and enabling more ambitious missions. Communication networks are essential. Spacecraft at asteroids need to send data back to Earth and receive instructions, even if those instructions are only periodic updates to their autonomous routines. NASA's Deep Space Network, a collection of large radio antennas spread across the globe, currently handles communications for interplanetary missions. However, this network is already heavily tasked, supporting missions to Mars, the outer planets, and beyond. Adding multiple asteroid mining missions would strain its capacity. Private companies might build their own ground stations, or collaborate to create a shared network. Alternatively, relay satellites positioned strategically in space could forward signals, reducing the burden on ground-based antennas. Some proposals even suggest using laser-based optical communication, which can carry more data than radio but requires precise pointing and is more susceptible to interference from dust or plasma. Navigation and tracking infrastructure helps ensure spacecraft know where they are and where they're going. In Earth orbit, GPS provides precise positioning, but GPS satellites don't reach beyond our immediate vicinity. Asteroids are tracked from Earth using telescopes, but knowing a spacecraft's position relative to an asteroid requires onboard sensors and triangulation. Some missions carry star trackers, cameras that identify constellations and calculate orientation. Others use radar or lidar to measure distance to the asteroid's surface. Ground-based tracking from Earth provides a cross-check, using radio signals to determine the spacecraft's position and velocity. Coordinating all these systems and ensuring data is accurate and timely requires careful planning and international cooperation. Asteroid mining missions would benefit from improved tracking networks, possibly including dedicated space-based observatories that monitor both natural asteroids and active spacecraft. Processing and manufacturing facilities might eventually move into space. Imagine a station in lunar orbit or at a gravitationally stable Lagrange point, equipped to refine metals, purify water, and manufacture components. Such a facility could serve multiple asteroid mining missions, accepting raw material from various sources and producing refined products for sale or further use. Building such a station would be expensive, but it could be amortized across many missions and even serve other space industries. The Moon itself might host surface facilities, using lunar regolith and water ice to support operations. Material from asteroids could be shipped to the Moon for processing, leveraging lunar gravity to simplify certain refining techniques. Over time, a cislunar economy could develop, with the Moon, Earth orbit, and nearby asteroids forming an interconnected industrial zone. Legal and regulatory infrastructure is less tangible but no less important. Space law, primarily governed by the Outer Space Treaty of 1967, establishes that no nation can claim sovereignty over celestial bodies. However, the treaty is ambiguous about resource extraction. Can a company own the platinum it mines from an asteroid, even if it can't own the asteroid itself? The United States and Luxembourg have both passed national laws affirming that companies can own resources they extract from space, but international consensus remains elusive. Without clear legal frameworks, investors face uncertainty. What if another nation disputes a claim? What if competing companies target the same asteroid? Establishing property rights, dispute resolution mechanisms, and environmental guidelines for space will require international negotiation, a slow and politically fraught process. Financial infrastructure supports investment and trade. Asteroid mining companies need capital, and investors need assurance that their money is being used responsibly and that returns are plausible. Stock markets, venture capital, government grants, and international development banks could all play roles. Some governments might offer incentives, such as tax breaks or guaranteed purchase agreements for space-derived materials. Insurance markets would need to develop products tailored to the unique risks of asteroid mining. Launch failures, equipment malfunctions, market fluctuations, and even the possibility of international conflict over resources. Futures markets for asteroid-derived platinum or water could emerge, allowing companies to hedge against price changes and investors to speculate on the future of the industry. Workforce and education infrastructure rounds out the picture. Asteroid mining requires engineers, scientists, mission controllers, data analysts, legal experts, and business managers, all with specialized knowledge. Universities and training programs must adapt to prepare people for these roles. Some skills transfer from terrestrial mining, aerospace, or robotics, but others are entirely new. Remote operation of autonomous systems, long-duration mission planning, and the economics of space resources are niche fields that will need to grow. International collaboration could help, pooling expertise and distributing the educational burden across nations. Building this infrastructure is a collective effort, one that extends beyond any single company or country. It represents an investment in the future, a recognition that space is becoming an arena for commerce and industry. The roads to riches in asteroid mining are not yet paved, but the surveying has begun, and the first stones are being laid. Progress will be gradual, measured in decades rather than years, but each new capability brings the dream a little closer to reality. Now we turn to the question of markets, where value is realized and economics truly comes into play. Part 5. The market question. Value, in the end, is not determined by what something costs to produce or how rare it might be in absolute terms. Value is determined by what someone is willing to pay, and that depends on supply, demand, and the existence of alternatives. This is the central tension in asteroid mining economics. Even if we successfully extract tons of platinum from an asteroid and bring it to Earth, what happens to the market when such a quantity appears? The answer is complex, and it shapes every business plan and investment thesis in the industry. Platinum, to take one example, is currently priced around $30 per gram, fluctuating with industrial demand and geopolitical factors. Annual production from terrestrial mines totals roughly 200 tons globally. Now imagine a single asteroid mining mission returns 10 tons of platinum, 5% of the annual supply, in a single year. If that material enters the market all at once, prices would likely drop as supply overwhelms demand. How much they drop depends on demand elasticity, the degree to which buyers increase their consumption as prices fall. Platinum is used in catalytic converters, but electric vehicles don't need them, and the automotive industry is shifting. Demand from jewelry and investment exists, but it's limited. Industrial uses in chemical processing and electronics could absorb some additional supply, but not infinite amounts. A sudden glut could crash prices, turning a potentially profitable mission into a financial disaster. This problem is well understood by anyone contemplating asteroid mining. The solution most often proposed is gradual introduction of materials. Rather than flooding the market, a mining company would release platinum in controlled amounts, maintaining prices and maximizing revenue over time. This approach resembles how diamond companies have historically managed supply to keep prices high. It requires market discipline, either through monopoly control or coordination among multiple producers. In a competitive market with several asteroid mining companies, such coordination might be difficult or illegal under antitrust laws. A race to sell could ensue, with each company trying to offload material before prices fall too far, which would only accelerate the crash. The first companies to succeed in asteroid mining will face strategic decisions about how to manage their market impact. Alternatively, asteroid mining could target materials where demand is large or growing and where alternatives are limited. Rare earth elements are one possibility. Global demand for rare earths is rising due to renewable energy technologies, electric vehicles, and advanced electronics. China's dominance of the supply chain creates geopolitical risks and price volatility. A new source of rare earths from asteroids could diversify supply and reduce dependence on any single nation. However, rare earths are not particularly rare in the Earth's crust. They're just difficult and environmentally damaging to refine. If asteroid mining can deliver refined rare earths at competitive prices, it might find a market. But if the cost of space mining exceeds the cost of developing new terrestrial mines with better environmental controls, the market will choose the cheaper option. Water represents a different market altogether. Water in space is valuable not for consumption on Earth, where it's abundant, but for use in space. Rockets require propellant, and water can be split into hydrogen and oxygen, the components of highly efficient rocket fuel. If water from asteroids can be delivered to orbital depots or lunar bases at a lower cost than launching it from Earth, demand could be substantial. This market depends on the growth of the space economy. More satellites, more crewed missions, more lunar and Martian exploration, all increase demand for propellant. Some forecasts predict thousands of tons of propellant needed annually by the 2040s if space activity continues to expand. Asteroid-derived water could supply this demand, creating a robust market without ever touching Earth. The emergence of a space-based economy is speculative but increasingly plausible. SpaceX, Blue Origin, and other companies are developing infrastructure for space tourism, manufacturing, and even habitation. Space stations in low Earth orbit might host research labs, factories producing specialized materials in microgravity, or hotels for tourists. These facilities need supplies: air, water, food, construction materials, spare parts. Launching everything from Earth is expensive. Sourcing materials from the Moon or asteroids could be cheaper, especially for bulk items like water or structural metals. This creates a feedback loop. Asteroid mining supports space infrastructure, which in turn increases demand for asteroid resources. Market absorption is another consideration. Even if demand is robust, how quickly can an industry integrate new supply? Factories using platinum must have the capacity to process it. Electronics manufacturers using rare earths must adjust their supply chains. Water depots in space must be built before asteroid-derived water can be sold. The market for asteroid resources will grow organically as infrastructure develops and industries adapt. Pushing supply ahead of demand risks losses, while waiting for demand to mature risks allowing competitors to seize the opportunity. Timing is everything. Competition from terrestrial sources cannot be ignored. Mining companies on Earth are not static. If asteroid mining threatens their market share, they will innovate, reducing costs or improving extraction methods. Environmental regulations might tighten, making asteroid mining's cleaner footprint more attractive, or they might relax, giving terrestrial miners breathing room. Technological advances such as asteroid mining could also spur similar advances on Earth, keeping terrestrial mining competitive. The interplay between space and terrestrial industries will shape market dynamics in unpredictable ways. Speculation and investment markets add volatility. Even before a single gram of asteroid material is sold, companies involved in asteroid mining are traded on stock exchanges. Their valuations reflect investor expectations about future profits, which are based on assumptions, models, and optimism. If a mission succeeds, stock prices might soar. If a mission fails, they could collapse. This volatility attracts speculators, people betting on outcomes rather than investing in long-term fundamentals. Such speculation can provide capital when needed, but it can also distort decision-making, pushing companies toward risky, headline-grabbing moves rather than steady, sustainable progress. Monopoly versus competition is a recurring theme. If one company or consortium achieves a breakthrough and establishes dominance, they could control prices and supply, extracting maximum profit. This might fund further expansion but could also stifle competition and slow innovation. Conversely, a competitive market with multiple players would drive efficiency and lower costs, benefiting customers but potentially squeezing profit margins so thin that investment becomes unattractive. Regulatory bodies and international agreements might intervene, either to prevent monopolies or to ensure fair access to asteroid resources. The market structure that ultimately emerges will depend on legal, economic, and political forces that are only beginning to take shape. The market question, then, is multi-layered. It's not enough to extract resources. Those resources must find buyers at prices that justify the effort. It's not enough to have buyers. The market must absorb supply without collapsing. And it's not enough to understand today's market. Asteroid mining operates on timescales where demand, technology, and competition will all evolve in ways we can only partially foresee. Navigating these uncertainties requires not just engineering and capital, but also strategic insight, patience, and a willingness to adapt as circumstances change. Part 6. The Pioneers and Their Plans. Several companies and organizations have declared ambitions to mine asteroids, each with different strategies and timelines. Their stories reveal both the allure of asteroid mining and the hard realities that temper enthusiasm. Understanding who these pioneers are, and what they've attempted, helps ground the economics in real-world challenges rather than pure speculation. Planetary Resources was among the first to capture public attention. Founded in 2009 and publicly announced in 2012, the company attracted high-profile investors and advisors, including filmmaker James Cameron and Google executives. Their plan involved launching small telescopes to identify and characterize near-Earth asteroids, followed by prospecting missions and eventually extraction. They launched test satellites to demonstrate technology, but progress was slow and funding proved difficult to sustain. The company was acquired by a blockchain firm in 2018 and effectively ceased asteroid mining operations. Their vision was bold, but the gap between concept and commercial viability proved too wide to cross with available resources. Deep Space Industries took a similar approach, announcing plans for prospecting missions and harvesting water from asteroids. They developed concepts for small spacecraft that could rendezvous with asteroids and extract volatiles. Like Planetary Resources, they struggled to secure sustained funding. The company was acquired by Bradford Space in 2019, shifting focus away from mining toward other space technologies. These early failures taught the industry important lessons about the need for patience, realistic timelines, and revenue streams that could sustain operations before mining itself became profitable. NASA has pursued asteroid science and sample return missions rather than commercial mining. The OSIRIS-RX mission successfully collected samples from the asteroid Bennu and returned them to Earth in 2023, providing invaluable data about asteroid composition and structure. Japan's Hayabusa 2 mission similarly returned samples from Ryugu. These missions cost hundreds of millions of dollars and took years to complete, demonstrating both the feasibility of reaching asteroids and the expense involved. While not commercial ventures, they advance technology and knowledge that future mining companies will rely upon. Luxembourg positioned itself as a supportive jurisdiction for space resource ventures, passing laws in 2017 to provide legal certainty for companies extracting space resources. The government established a space agency and offered funding to encourage companies to base operations there. Several asteroid mining and related ventures established offices in Luxembourg, attracted by the favorable legal environment and financial support. This national strategy reflects recognition that space resources could become economically significant, and that early regulatory clarity might attract industry. The United States passed the Commercial Space Launch Competitiveness Act in 2015, affirming that American citizens and companies have rights to resources they extract from asteroids. This law provides some legal foundation, though international recognition remains incomplete. Other nations have watched these developments, some with interest and others with concern about potential conflicts over space resources. Trans-Astra Corporation has focused on optical mining technology, using concentrated sunlight to excavate and process asteroid material. Their approach involves large inflatable reflectors that focus sunlight onto the asteroid surface, heating it to release volatiles or melt rock. This method requires minimal mechanical equipment and could be lighter and more reliable than drills or scoops. Trans-Astra has received NASA funding for technology development and continues to refine their concepts, though commercial operations remain years away. Companies like SpaceX and Blue Origin, while not focused specifically on asteroid mining, are developing infrastructure that could enable it. Reusable rockets, orbital refueling capabilities, and deep space transport systems lower the barriers to reaching asteroids. As these companies pursue their own goals, lunar exploration and Mars colonization, they create capabilities that asteroid mining ventures can leverage. China's space program has expressed interest in asteroid exploration and resource utilization as part of broader ambitions in space. While details remain limited, Chinese officials have discussed missions to near-Earth asteroids and the development of technologies for in-space resource processing. If China pursues asteroid mining, it could accelerate international competition and complicate the legal landscape. The pioneers face a common challenge: bridging the gap between promising technology and profitable operations. Early ventures underestimated the timeline and capital required. Current efforts are more cautious, focusing on incremental technology development and seeking diverse revenue sources. Some companies provide services to government space agencies, using that income to fund their own research. Others develop technologies applicable to both asteroid mining and other space ventures, spreading risk across multiple markets. The path forward likely involves public-private partnerships, where governments fund early exploration and technology demonstration while private companies develop commercial applications. Part 7. Costs, Timelines, and Breakeven. Estimating the cost of asteroid mining is difficult because no one has done it yet. Analysts construct models based on comparable projects, engineering estimates, and assumptions about technology development. These models provide ranges rather than precise figures, and they vary widely depending on assumptions. Still, they offer insight into the scale of investment required and the conditions under which profitability might be achieved. A credible estimate for a first asteroid-mining mission, including spacecraft development, launch, operations, and material return, falls somewhere between $3 and $10 billion. This figure assumes use of mostly existing technology, modest scale, and a near-Earth asteroid target. Optimistic scenarios, leveraging rapid advances in reusable rockets and miniaturized spacecraft, might reduce costs to $1 or $2 billion. Pessimistic scenarios, accounting for technical setbacks and cost overruns, could push the figure above $15 billion. For comparison, NASA's OSIRIS-RX mission cost roughly $1 billion and returned only a few hundred grams of material. Scaling up to commercial quantities multiplies complexity and expense. Launch costs are a significant component. A mining spacecraft with extraction equipment, processing systems, and propellant might mass 50 to 100 tons. At current launch prices of $2,500 per kilogram, that's $125 to $250 million just to reach orbit. If assembly in orbit is required, multiple launches drive costs higher. Future systems like Starship promise lower costs, potentially under $100 per kilogram, which would reduce launch expenses dramatically. However, such systems are not yet operational at that price point, and relying on future cost reductions introduces uncertainty. Development costs for mining equipment, spacecraft systems, and autonomous operations software could reach $1 to $3 billion. Designing hardware that functions reliably in space, testing it, and qualifying it for flight is expensive. Companies must build prototypes, conduct ground tests, and possibly fly technology demonstration missions before committing to a full-scale operation. Each development cycle takes years and consumes capital without generating revenue. Operational costs accumulate throughout the mission. Mission control teams monitor spacecraft, analyze data, and send instructions. Ground stations communicate with the spacecraft. Insurance premiums protect against launch failures and operational risks. If the mission lasts 5 years from launch to material return, operational costs might total $100 to $300 million. Longer missions increase this burden. Material return costs depend on the approach. Small capsules designed to survive reentry might cost tens of millions each to develop and deploy. If multiple return trips are needed, costs multiply. Alternatively, if material is sold in space rather than returned to Earth, transport costs are lower but market opportunities are currently limited. Given these costs, what must a mission return to break even? If total costs are $5 billion and the target is platinum, the mission must return enough platinum to cover that investment plus any desired profit. At $30 per gram, $5 billion requires roughly 167,000 kilograms of platinum, or 167 tons. That's roughly the entire annual global production of platinum. Selling that much without crashing prices is implausible. This simple calculation reveals the central problem. The economics work only if costs drop dramatically, if higher value materials are targeted, or if non-terrestrial markets develop. Some models suggest focusing on the space market first. Water sold in orbit for propellant might fetch $1,000 per kilogram or more, given the cost of launching it from Earth. A mission returning 1,000 tons of water could generate $1 billion in revenue. If costs are kept to $2 billion, multiple missions could eventually become profitable as efficiency improves and infrastructure is reused. This approach requires patience and assumes demand grows as space activity expands. Timelines for achieving profitability stretch decades into the future. Optimistic projections suggest the first profitable asteroid mining mission might occur in the late 2030s, assuming steady technology progress and growing space markets. More conservative estimates push this to the 2050s or beyond. The first missions will likely operate at a loss, serving as technology demonstrators and data sources for improving subsequent missions. Only after several iterations, as costs fall and operational experience accumulates, might profitability emerge. Risk-adjusted returns are another consideration. Investors compare asteroid mining to other opportunities. If a $5 billion investment might return modest profit in 20 years, that's unattractive compared to safer investments with quicker returns. Asteroid mining must offer exceptional upside potential to justify the risk and delay. This could come from capturing a new market, achieving monopoly control over certain resources, or benefiting from unforeseen developments that drive demand higher than expected. Part 8. Geopolitics and strategic resources. Asteroid mining is not purely a commercial venture. It carries geopolitical weight, raising questions about national security, resource independence, and international power dynamics. Governments recognize that control over strategic materials influences economic strength and military capability. Rare earth elements, for instance, are critical for defense systems, and dependence on foreign suppliers creates vulnerability. Asteroid mining offers a potential path to resource independence, a possibility that attracts attention from policymakers and military planners. China's dominance in rare earth production and processing gives it leverage over global supply chains. While rare earths exist in other countries, China controls refining capacity and can restrict exports to advance political goals. The United States and allied nations have sought to diversify supply, investing in domestic mining and processing. Asteroid-derived rare earths could supplement these efforts, providing supply that no terrestrial nation controls. However, this assumes asteroid mining becomes economically viable and operates at sufficient scale, conditions not yet met. Platinum group metals have strategic importance beyond industrial use. They're essential for certain military applications and advanced technologies. A nation that secures abundant supplies gains advantages in manufacturing and innovation. If asteroid mining achieves commercial success, early movers could dominate supply, shaping markets and influencing international relations. This prospect has prompted some governments to support domestic asteroid mining companies through funding, legal frameworks, and diplomatic efforts. Space law and international agreements will play crucial roles. The Outer Space Treaty prohibits national appropriation of celestial bodies but is ambiguous about resource extraction. Some argue that extracting resources without claiming sovereignty is permissible. Others contend that significant resource extraction constitutes de facto appropriation, violating the treaty's spirit. International consensus on this issue is lacking, creating legal uncertainty that complicates investment and operations. The Moon Agreement of 1979 attempted to address resource issues, declaring that celestial resources are the common heritage of mankind and should be managed internationally. However, few nations ratified this agreement, and major spacefaring countries including the United States, Russia, and China did not sign. Without broad acceptance, the Moon Agreement has limited impact. New agreements or amendments to existing treaties may be necessary to establish clear rules for asteroid mining. Conflict over asteroid resources is a conceivable risk. If multiple nations or companies target the same asteroid, disputes could arise. Without mechanisms for resolving such disputes, tensions might escalate. Some scenarios envision military posturing or even conflict in space, though most analysts consider this unlikely in the near term. Establishing norms for claiming mining rights, perhaps through registration systems or international licensing, could reduce conflict risk. Institutions like the United Nations Committee on the Peaceful Uses of Outer Space could facilitate negotiations, though reaching agreement among diverse nations with competing interests is challenging. Resource nationalism might emerge in space as it has on Earth. Nations could assert that asteroids discovered or surveyed by their spacecraft belong to them, creating exclusive economic zones around celestial bodies. Such claims would likely face opposition from other nations and could undermine the principle of space as a global commons. Balancing national interests with international cooperation will require diplomatic skill and willingness to compromise. Strategic competition in space extends beyond resources. Capabilities developed for asteroid mining, such as deep space propulsion, autonomous robotics, and resource processing, have potential military applications. Governments monitor these developments, concerned about rivals gaining technological advantages. Dual-use technologies complicate arms control and confidence-building measures. Transparency about intentions and capabilities could ease concerns, but competition and secrecy often prevail. Part 9. Legal frameworks and property rights. The question of who owns what in space remains unsettled, and this uncertainty casts a shadow over asteroid mining economics. Investors hesitate when property rights are unclear. Companies struggle to plan when legal frameworks are incomplete. The body of space law that exists today was written decades ago, in a different era with different priorities, and it does not neatly address commercial resource extraction. The Outer Space Treaty of 1967 forms the foundation of international space law. Negotiated during the Cold War, it establishes that outer space, including celestial bodies, is the province of all mankind. No nation can claim sovereignty over the Moon, asteroids, or other celestial objects. Weapons of mass destruction are prohibited in space. Nations bear responsibility for their space activities, including those of private companies. These principles have kept space relatively peaceful, but they create ambiguity for resource extraction. If no one owns an asteroid, can anyone own the platinum they extract from it? Most legal scholars argue that the treaty prohibits claiming territory but not extracting resources. The analogy often used is fishing in international waters. No nation owns the ocean, but fishermen can catch and sell fish. Similarly, no nation owns an asteroid, but a company might extract and sell its minerals. This interpretation allows for commercial activity while respecting the treaty's principles. However, Not everyone agrees. Some nations and commentators argue that large-scale extraction constitutes appropriation, violating the spirit if not the letter of the treaty. The United States addressed this issue domestically with the Commercial Space Launch Competitiveness Act of 2015. This law states that American citizens and companies are entitled to any resources they obtain from asteroids, including ownership, transport, and sale. Luxembourg passed similar legislation in 2017, as did the United Arab Emirates in 2019. These national laws provide some certainty for companies operating under those jurisdictions, but they do not resolve international disagreements. A resource claim recognized in Washington or Luxembourg might not be recognized in Beijing or Moscow. The Moon Agreement of 1979 took a different approach, declaring celestial resources the common heritage of mankind and proposing international management. Few countries ratified this agreement. Major spacefaring nations, including the United States, Russia, and China, did not sign. Without broad support, the Moon Agreement has little practical effect, but it reflects ongoing debate about whether space resources should be governed collectively or exploited competitively. Property rights matter because they enable investment. Investors need assurance that the resources a company extracts will belong to that company, not be seized by competitors or governments. Without clear ownership, financing becomes difficult. Banks and venture capitalists demand predictability. Uncertainty raises risk, and higher risk demands higher returns, which makes projects less attractive. Establishing an international framework for resource rights would reduce this uncertainty and facilitate investment. Several proposals for such frameworks exist. One approach involves registration systems, where companies register their claims to specific asteroids with an international body. Registration would grant exclusive rights for a specified period, during which the company could explore and extract resources. Other companies would be prohibited from interfering. After the period expires, rights might revert to open access or be auctioned. This system resembles mining claims on public land in many countries. It balances exclusive rights needed for investment with the principle that space belongs to everyone. Another approach emphasizes freedom of access and first-come rights. Under this model, any company that reaches an asteroid and begins extraction has rights to the material they extract, but no exclusive claim to the asteroid itself. Other companies could work on the same asteroid, provided they do not interfere with existing operations. This approach minimizes bureaucracy but could lead to conflicts if multiple operators crowd a single asteroid. Coordination and dispute resolution mechanisms would be essential. Environmental considerations are beginning to enter the conversation. While asteroids have no ecosystems to protect, some argue for preserving certain objects for scientific study. Asteroids provide insights into the solar system's formation and evolution. Mining could destroy or contaminate these natural archives. Designating some asteroids as protected reserves, off-limits to commercial activity, might balance scientific and commercial interests. Deciding which asteroids to protect, and enforcing those protections, requires international agreement and monitoring capabilities. Liability is another legal concern. The Outer Space Treaty holds nations responsible for damage caused by their space activities. If an asteroid mining operation goes wrong, causing debris that damages a satellite or injures people. Who pays? The launching nation is liable, but they may seek reimbursement from the company responsible. Insurance can cover some risks, but catastrophic failures might exceed policy limits. Clear liability rules encourage responsible behavior and ensure victims can seek compensation. The legal landscape for asteroid mining is evolving slowly. International negotiations on space resource governance have occurred through the United Nations and other forums, but consensus remains elusive. Different nations have different priorities and concerns. Some prioritize economic opportunity and want minimal regulation. Others emphasize equitable benefit sharing and environmental stewardship. Bridging these divides takes time, and meanwhile, companies proceed under national laws and hope international frameworks will eventually catch up. This approach is pragmatic but risky. Legal clarity would accelerate investment and reduce conflict, making it a crucial piece of the asteroid mining puzzle. Part 10. Environmental and ethical dimensions. Asteroid mining is often portrayed as environmentally friendly, a way to obtain resources without scarring Earth's landscape or polluting its air and water. There is truth to this claim, but the full picture is more nuanced. The environmental and ethical dimensions of asteroid mining deserve careful consideration, even if they seem distant concerns compared to immediate economic and technical challenges. Terrestrial mining causes significant environmental harm. Open-pit mines strip away vegetation and soil, creating massive scars visible from space. Tailings, the waste rock and chemicals left after extracting valuable minerals, can contaminate waterways and soil. Acid mine drainage poisons ecosystems for decades. Smelting and refining release greenhouse gases and toxic pollutants. Mining also displaces communities, destroys habitats, and consumes vast amounts of water and energy. If asteroid mining can provide the same materials without these impacts, the environmental benefit is substantial. However, asteroid mining is not impact-free. Launching rockets burns large quantities of propellant, releasing carbon dioxide and other emissions. Current launch rates are small enough that their climate impact is negligible, but a major expansion of space activity could change that. Thousands of launches annually would contribute measurably to atmospheric pollution and climate change. Developing cleaner propellants or carbon-neutral launch systems would mitigate this concern, but such technologies are not yet widespread. Space debris is another environmental issue, though it affects the space environment rather than Earth's biosphere. Failed missions, discarded rocket stages, and collisions create debris that orbits Earth, posing hazards to satellites and spacecraft. Asteroid mining missions must be designed to minimize debris creation. Spacecraft should be deorbited at end of life or moved to graveyard orbits where they will not interfere with active zones. International guidelines on debris mitigation exist, but enforcement is weak. Responsible operators follow best practices voluntarily, but not all do. The asteroids themselves raise questions. Should we preserve some asteroids for scientific study, treating them as natural heritage sites? Asteroids hold clues to the solar system's origins, and mining could destroy evidence before scientists fully study it. Designating certain asteroids as reserves, protected from commercial activity, is one solution. Scientists could prioritize these for study while industry focuses on others. Deciding which asteroids to protect and enforcing those protections requires international coordination. Ethical questions extend beyond environment. Who benefits from asteroid mining? If a single company or nation captures the wealth, does that violate the principle that space is the province of all mankind? Some argue that asteroid resources should be shared globally, with profits funding development projects or distributed as a universal dividend. Others contend that those who take the risks and make the investments deserve the rewards, just as in any business venture. Balancing private gain with public good is a perennial challenge in resource industries, and asteroid mining will be no exception. The concentration of wealth and power is a concern. If asteroid mining succeeds, it could create immense fortunes for early participants. This might exacerbate inequality, concentrating resources in the hands of a few individuals or nations. On the other hand, asteroid mining could democratize access to materials, lowering prices and making technology more affordable for everyone. The outcome depends on how the industry develops, how markets function, and how governments regulate and tax space commerce. Employment and labor issues are distant but worth considering. Will asteroid mining create jobs? Or will it be so automated that few people benefit directly? Terrestrial mining employs millions globally, often in regions with limited alternatives. If asteroid mining displaces terrestrial mining, those workers and communities could suffer. Transition assistance, retraining programs, and economic diversification could ease the impact, but such measures require foresight and political will. Cultural and philosophical dimensions also matter. Asteroids are part of humanity's shared cosmic heritage. Mining them is a significant step in our relationship with the universe, transforming us from passive observers into active shapers of the solar system. Some see this as inspiring, a sign of progress and ambition. Others find it troubling, a continuation of extractive, exploitative patterns that have harmed Earth. These perspectives shape public opinion and political debates, influencing whether asteroid mining receives support or faces opposition. Indigenous voices have entered space discussions, noting that colonization of space risks repeating injustices experienced on Earth. Treaties and laws should be designed with input from diverse communities, not just spacefaring nations and corporations. Ensuring that asteroid mining benefits humanity broadly, rather than a privileged few, requires inclusive decision-making and equitable frameworks. The environmental and ethical dimensions of asteroid mining are not obstacles to be overcome but considerations that shape how the industry should develop. Done thoughtfully, asteroid mining could provide resources while minimizing harm. Done carelessly, it could replicate the worst aspects of terrestrial extraction. The choices made now, as the industry takes its first steps, will echo for generations. Part 11. The role of governments and policy. Governments play multiple roles in asteroid mining. They fund research, provide legal frameworks, regulate safety and environmental standards, and sometimes invest directly in ventures. Their involvement can accelerate development or hinder it, depending on how policies are designed and implemented. Understanding the government role helps clarify the path from today's experiments to tomorrow's industry. Funding for space exploration has traditionally come from government budgets. NASA, ESA, JAXA, and other space agencies invest billions in missions that advance knowledge and technology. Asteroid sample return missions like OSIRIS-RX and Hayabusa 2 were publicly funded, and their findings benefit everyone, including commercial ventures. Governments justify these expenditures as public goods, investments in science and technology that private companies might not make on their own. Data from these missions inform asteroid mining plans, reducing risk and uncertainty for private investors. Some governments provide direct support to asteroid mining companies. Luxembourg established a space resources program offering grants and equity investments to companies willing to base operations there. The United Arab Emirates created similar incentives. These programs aim to position small nations as leaders in emerging space industries, diversifying their economies beyond traditional sectors. The strategy is risky, as asteroid mining remains unproven, but the potential payoff is substantial if the industry takes off. Tax policy influences investment decisions. Governments might offer tax credits for research and development, or reduced rates for space resource companies. Such incentives lower effective costs, making marginal projects viable. Conversely, taxes on asteroid-derived materials could fund public programs or compensate for environmental impacts. Striking the right balance encourages industry growth without sacrificing public revenue. Regulatory frameworks ensure safety and minimize harm. Launch licenses, spectrum allocation for communications, and orbital slot assignments all require government approval. Companies must demonstrate that their missions comply with safety standards and international obligations. While regulation can feel burdensome, it also provides structure and predictability that markets need. Clear rules about what is allowed and what is prohibited help companies plan and investors assess risk. International cooperation and competition both shape government policy. Space treaties are negotiated multilaterally, requiring consensus among nations with diverse interests. The Artemis Accords, a recent initiative led by the United States, seek to establish norms for lunar and asteroid resource use. Signatories agree to principles like transparency, interoperability, and peaceful use. Not all nations have signed, and some view the accords as an attempt to set rules without broad international input. Tensions between cooperative and competitive approaches will influence how asteroid mining develops globally. Military and security considerations cannot be ignored. Technologies developed for asteroid mining have potential military applications. Autonomous robotics, advanced propulsion, and in-space manufacturing could support defense systems or space-based infrastructure. Governments monitor these developments closely, sometimes supporting them for strategic reasons. The overlap between civilian and military space capabilities complicates arms control and raises concerns about weaponization of space. Public opinion influences government policy. If citizens view asteroid mining as an exciting opportunity, governments may support it enthusiastically. If concerns about environmental impact, inequality, or militarization dominate, support may be tepid or conditional. Engaging the public, explaining benefits and risks honestly, and incorporating feedback into policy design helps build sustainable support. The role of government in asteroid mining will evolve. Early stages may require substantial public investment to develop foundational technologies and knowledge. As the industry matures, private capital might take the lead, with government shifting to regulatory oversight and international coordination. This transition mirrors patterns in other industries, from aviation to telecommunications. The key is ensuring that government involvement supports innovation without stifling it, protects public interests without micromanaging, and balances national ambitions with international responsibilities. Getting this balance right will determine whether asteroid mining fulfills its promise or founders under the weight of bureaucracy and conflict. Part 12. Risk and uncertainty. Every business venture carries risk, but asteroid mining operates at the extreme end of the spectrum. The uncertainties are profound, spanning technology, markets, law, and even basic geology. Understanding these risks is essential for anyone considering investment or involvement in the industry. Some risks can be managed or mitigated. Others must simply be accepted as the price of pioneering. Technical risk tops the list. Spacecraft can fail during launch, destroying years of work and hundreds of millions of dollars in seconds. Even if launch succeeds, the journey to an asteroid is long and filled with hazards. A software glitch, a micrometeorite strike, or a component failure could cripple the mission. Redundancy and robust design help, but they add weight and cost. The history of space exploration is littered with failures, and even well-funded, expertly managed missions sometimes go wrong. Mars missions, for example, have a success rate around 50%. Asteroid missions might fare better with improved technology, but risk remains. Asteroid characterization presents geological uncertainty. Remote observations from Earth provide limited information about an asteroid's composition and structure. An asteroid that looks metallic from spectroscopic analysis might turn out to be a rubble pile coated in metal-rich dust. Water content estimated at 10% might actually be 2%, rendering extraction uneconomical. Only direct sampling and detailed surveys can confirm what an asteroid truly contains, and those activities happen late in the mission timeline, after significant capital has been committed. Extraction technology remains unproven at commercial scale. Laboratory tests and small-scale demonstrations are promising, but scaling up to industrial quantities introduces new challenges. Equipment might jam, overheat, or wear out faster than expected. Processing efficiency might fall short of models. These problems can often be solved, but solutions take time and money, extending timelines and eating into budgets. The first missions will inevitably encounter surprises, and how quickly teams adapt will determine success or failure. Market risk looms large. Even if everything technical goes perfectly, market conditions at the time of material return might be unfavorable. Platinum prices could have fallen due to reduced demand or increased terrestrial supply. The space economy might develop more slowly than anticipated, leaving no buyers for asteroid-derived water. Economic recessions, technological disruptions, or geopolitical events could shift markets in unpredictable ways. Long lead times between investment and return amplify this risk. A decision made today is based on assumptions about markets a decade or more in the future. Regulatory and legal risks add another layer. Governments might change laws, imposing new taxes or restrictions on asteroid mining. International disputes over resource rights could tie up operations in legal battles. Environmental regulations, though currently minimal for space activities, might tighten if public concern grows. Companies must navigate a patchwork of national laws and uncertain international norms, adapting as the legal landscape evolves. Financial risk affects both companies and investors. Asteroid mining requires sustained capital over many years. If funding dries up midway through a project, everything invested so far could be lost. Companies must manage cash flow carefully, balancing expenditures against available capital. Investors must be prepared for the possibility of total loss, a real risk in such a speculative industry. Diversification can spread risk, but it also dilutes focus and expertise. Competition introduces strategic risk. If multiple companies target the same asteroid or market, they might undercut each other, driving prices down and eroding profits. Conversely, a competitor's breakthrough could render a company's approach obsolete. Monitoring competitors, adapting strategies, and sometimes collaborating to share costs and risks are all necessary but complex endeavors. Geopolitical risk cannot be dismissed. International tensions could lead to sanctions, trade restrictions, or even conflict that disrupts operations. Access to launch facilities, communication networks, or key technologies might be restricted for political reasons. Companies operating internationally must navigate these sensitivities, maintaining good relations with multiple governments while protecting their interests. Reputational risk matters as well. A high-profile failure could damage investor confidence not just in one company but in the entire industry. Public perception influences government support and social license to operate. Companies must communicate honestly about progress and setbacks, managing expectations while maintaining credibility. Despite these risks, many are willing to proceed. Risk and reward are inseparable. The potential payoff from successful asteroid mining is enormous, and for some investors and entrepreneurs, that justifies the dangers. Risk management strategies, from insurance to phase development to diversified portfolios, help make uncertainty tolerable. The key is entering with eyes open, understanding that failure is a real possibility, and planning accordingly. Asteroid mining will not be for the risk-averse, but for those with vision, capital, and patience. The uncertainties are challenges to be navigated rather than barriers to be feared. Part 13. Synergies with space exploration. Asteroid mining does not exist in isolation. It connects to broader goals of space exploration and development, creating synergies that could accelerate progress across multiple fronts. Understanding these connections reveals how asteroid mining fits into humanity's larger ambitions in space and why governments and visionaries support it even before profitability is assured. Lunar exploration and asteroid mining share common technologies and interests. Both require efficient propulsion, autonomous robotics, and resource processing. Water extracted from lunar ice could fuel missions to asteroids, while asteroid-derived water could support lunar bases. Equipment developed for one application often works, with modifications for the other. This overlap allows costs and risks to be shared across programs, making each more viable than it would be alone. Mars missions could benefit significantly from asteroid resources. The journey to Mars requires enormous amounts of propellant. Launching all of it from Earth is expensive and limits mission scope. If spacecraft could refuel at an asteroid or from asteroid-derived propellant stored in orbit, Mars missions become cheaper and more flexible. Crew safety improves if emergency supplies can be cached along the route. Asteroid mining, then, is not just about extracting wealth but about building infrastructure that enables deeper exploration. Space-based manufacturing is another synergy. Factories in orbit or on the Moon could produce components for spacecraft, habitats, and other infrastructure. Raw materials from asteroids, metals, and silicates would feed these factories. Manufacturing in space avoids the cost of launching finished products from Earth and allows designs optimized for space rather than terrestrial gravity. This vision of a space-based industrial economy is speculative but increasingly discussed among engineers and planners. Scientific research benefits from asteroid mining activities. Prospecting missions gather data about asteroid composition, structure, and history. This information advances planetary science, helping us understand how the solar system formed and evolved. Mining operations might uncover unexpected findings, fossils of ancient processes or rare minerals. The relationship between science and commerce is symbiotic, each supporting the other. Space tourism and habitats create potential markets for asteroid resources. Hotels in orbit need water, air, and shielding from radiation. Construction materials for habitats could come from asteroids, reducing reliance on Earth-based supply chains. As tourism grows, demand for these resources will rise, providing revenue streams for asteroid mining companies. The timeline is uncertain, but the trend seems clear. Defense and security applications are more controversial but real. Capabilities developed for asteroid mining could support military or strategic objectives. Autonomous spacecraft, advanced propulsion, and resource independence are all valuable for national security. Some governments support asteroid mining partly for these reasons, viewing it as dual-use technology that serves both civilian and defense needs. This complicates international cooperation, as nations may be reluctant to share technologies with strategic implications. International collaboration in space exploration often involves shared missions and pooled resources. Asteroid mining could follow this model, with multiple nations contributing to a joint venture. Such collaboration spreads costs, combines expertise, and builds trust. The International Space Station is a precedent, demonstrating that cooperation is possible even among geopolitical rivals. Extending this spirit to asteroid mining could ease tensions and ensure benefits are widely shared. Inspiration and education are intangible but important synergies. Ambitious projects like asteroid mining capture public imagination, inspiring young people to pursue careers in science and engineering. Educational programs, documentaries, and public outreach raise awareness and build support. A society excited about space is more likely to fund exploration and tolerate the risks involved. The synergies between asteroid mining and broader space activities create a web of mutual reinforcement. Progress in one area enables progress in others. This interconnectedness means that asteroid mining should not be evaluated solely on its own economics but as part of a larger vision. If it helps humanity become a spacefaring civilization, its value extends beyond dollars and cents. Policymakers and investors increasingly recognize this, supporting asteroid mining not just for profit but for its role in opening the frontier. Part 14. Models and Scenarios. Economic models attempt to predict whether asteroid mining will be profitable and under what conditions. These models are built on assumptions, and small changes in those assumptions can swing outcomes dramatically. Examining different scenarios helps illustrate the range of possibilities and the factors that matter most. An optimistic scenario assumes rapid technological progress and growing space markets. Launch costs fall to $100 per kilogram as fully reusable rockets mature. Autonomous mining systems prove reliable, extracting resources efficiently with minimal human oversight. The space economy expands quickly, with thousands of satellites, lunar bases, and Mars missions creating demand for propellant and materials. In this scenario, a company investing $2 billion in an asteroid water mining mission could see returns within 10 years. Water sold at orbital depots fetches high prices, and repeat missions drive costs down through learning and reuse. Profitability emerges by the late 2030s, attracting more investment and accelerating growth. A pessimistic scenario paints a different picture. Launch costs plateau at current levels due to technical challenges or market saturation. Mining equipment proves less reliable than hoped, requiring expensive repairs and replacements. The space economy grows slowly, constrained by budgets and shifting priorities. Demand for asteroid resources remains negligible, and attempts to sell materials on Earth crash prices. In this scenario, a $5 billion mission yields minimal returns, and investors lose most of their capital. The industry stalls, with companies folding or pivoting to other ventures. Profitability, if it comes at all, is decades away. A middle scenario blends elements of both. Technology advances steadily but not spectacularly. Launch costs drop to $500 per kilogram, a significant improvement but not revolutionary. Mining systems work but require ongoing refinement. The space economy grows moderately, with government and commercial activities creating niche markets for asteroid resources. A mission costing $3 billion breaks even after 15 years, selling water to NASA and other customers. Follow-up missions improve economics, and by the 2040s, a small but viable industry exists. Growth is slow and profits modest, but the foundation is laid for future expansion. Sensitivity analysis reveals which variables matter most. Launch costs are critical. Reducing them by half can transform an unprofitable mission into a marginal one. Extraction efficiency is another key factor. If a system can extract twice as much water per unit of equipment, costs per kilogram drop significantly. Market price for asteroid resources also plays a major role. A doubling of water prices in space makes many more missions viable. Some models explore monopoly versus competitive scenarios. If one company achieves a breakthrough and dominates the market, they can set prices and maximize profit. This monopoly scenario is attractive for that company's investors but might slow overall industry growth if high prices limit demand. In a competitive scenario, multiple companies drive prices down, benefiting customers but squeezing margins. Competition spurs innovation and efficiency, but it also increases risk for any single company. Time value of money affects all models. Money invested today is worth more than money received in the future, due to opportunity costs and inflation. Asteroid mining's long timelines mean that future revenues must be substantial to justify present investments. Discount rates, the percentage used to calculate present value of future cash flows, significantly impact financial models. A high discount rate makes asteroid mining look less attractive, while a low rate improves the case. Scenarios involving catastrophic events, though unlikely, merit consideration. A major asteroid impact on Earth, ironically, could increase interest in asteroid mining by highlighting both the threat and the opportunity. Conversely, a high-profile mission failure with loss of life could trigger regulatory crackdowns and public backlash, chilling investment for years. Models are tools, not crystal balls. They structure thinking and highlight important factors, but they cannot predict the future. Actual outcomes will likely differ from any model, shaped by unforeseen developments and human choices. What models do provide is a framework for decision-making, helping investors, companies, and governments weigh options and allocate resources. By exploring scenarios, we prepare for a range of futures and remain adaptable as events unfold. The path to asteroid mining will win through unexpected terrain, and flexibility will be as valuable as any technical capability. Part 15. The human element. Behind the economics, technology, and policy lies a human dimension that shapes how asteroid mining unfolds. People make the decisions, take the risks, and ultimately determine whether this industry succeeds or fails. Understanding the motivations, challenges, and dynamics of the humans involved adds depth to the economic picture and reminds us that asteroid mining is not merely a technical problem but a human endeavor. Entrepreneurs driving asteroid mining ventures are often motivated by more than profit. Many express a deep passion for space exploration and a belief that humanity's future lies beyond Earth. They see asteroid mining as a stepping stone toward that future, a way to make space accessible and self-sustaining. This idealism attracts talent and inspires teams to persevere through setbacks. However, idealism alone does not pay bills or satisfy investors. Balancing vision with pragmatic business decisions is a constant challenge. Engineers and scientists working on asteroid mining face unique professional challenges. The work is highly specialized, requiring expertise in fields that barely existed a generation ago. Career paths are uncertain, as the industry is nascent and companies sometimes fail. Yet the intellectual challenge and the opportunity to work on cutting-edge problems attract some of the brightest minds. These individuals often accept lower salaries than they could earn elsewhere, compensated by the chance to contribute to something historically significant. Investors in asteroid mining range from billionaires funding passion projects to institutional investors seeking high-risk, high-reward opportunities. Their motivations vary. Some believe in the technology and want to be part of its development. Others see a chance for outsized returns if the industry takes off. Still others invest for strategic reasons, positioning themselves or their nations to benefit from future space resources. Managing these diverse stakeholders, with their differing timelines and expectations, requires skillful leadership. The workforce needed for asteroid mining extends beyond rocket scientists. Mission controllers, data analysts, legal experts, financial planners, public relations specialists, and many others all play roles. Training this workforce takes time, and retaining talent in a field with uncertain prospects is difficult. Companies must cultivate culture and purpose that keep employees engaged even when progress is slow and setbacks occur. Teamwork and collaboration are essential. Asteroid mining missions involve thousands of decisions, each requiring coordination among specialists. Engineers must work with scientists to interpret data. Business leaders must communicate with technical teams to understand what is feasible. International projects add layers of complexity, as teams from different countries bring different work styles, languages, and priorities. Building effective teams across these boundaries is as important as any technical achievement. Public perception and communication matter. How asteroid mining is presented to the world influences political support, investment, and social license to operate. Companies that communicate transparently, explaining both successes and failures honestly, build trust. Those that overpromise and underdeliver damage credibility, not just for themselves but for the industry. Engaging with journalists, educators, and the public helps build a constituency that supports space resource development. Ethical decision-making by individuals shapes the industry's character. Engineers deciding how to design systems, executives choosing which projects to pursue, and investors selecting which ventures to fund all make choices with ethical dimensions. Will they prioritize safety or cost? Will they respect environmental principles or cut corners? Will they engage with affected communities or ignore them? These individual choices aggregate into the industry's overall trajectory. Stress and burnout are real concerns. Space projects operate on timescales measured in years or decades. The intensity of work, the high stakes, and the constant pressure to perform can take a toll. Organizations that support their people with reasonable work-life balance, mental health resources, and recognition of achievements tend to perform better over the long run. Diversity and inclusion are increasingly recognized as strengths. Teams with varied backgrounds and perspectives solve problems more creatively and avoid groupthink. The space industry has historically been dominated by certain demographics, but efforts to broaden participation are underway. Bringing more women, people of color, and individuals from non-traditional backgrounds into asteroid mining will enrich the field and ensure it reflects the humanity it serves. Leadership will determine success or failure. Leaders must inspire teams, manage resources wisely, navigate political and regulatory landscapes, and maintain vision while adapting to reality. They must make difficult decisions under uncertainty, balancing competing interests and accepting responsibility for outcomes. The quality of leadership in asteroid mining companies and supporting institutions will shape whether the industry flourishes or flounders. The human element in asteroid mining is easy to overlook when focusing on technology and economics, but it is fundamental. Machines do not decide to explore asteroids. People do. Understanding their motivations, supporting their work, and fostering the right culture and values will be as important as any engineering breakthrough. Asteroid mining is ultimately a human story, and its success depends on the creativity, perseverance, and integrity of those who pursue it. Part 16. Alternative Futures. The future of asteroid mining is not predetermined. Multiple pathways are possible, each leading to different outcomes. Exploring these alternative futures helps us understand the contingencies and choices that will shape what actually happens. Some futures are hopeful, others cautionary, and most lie somewhere between. One future sees asteroid mining becoming a cornerstone of a thriving space economy. By the 2040s, dozens of missions are underway, extracting water, metals, and rare elements. Orbital depots stock propellant for missions heading to the Moon, Mars, and beyond. Manufacturing facilities in lunar orbit use asteroid-derived metals to build spacecraft components and habitats. Launch costs have fallen to levels that make space accessible to many nations and companies. Earth benefits from reduced environmental impact as some mining shifts off-world. Wealth generated from space resources funds development projects globally. International cooperation, though imperfect, manages conflicts and ensures benefits are broadly shared. This optimistic future is possible but requires sustained effort, wise policy, and fortunate timing. Another future sees asteroid mining stalling after initial enthusiasm. A few high-profile missions are attempted in the 2030s but encounter technical failures or cost overruns. Investors lose confidence, and capital dries up. Companies pivot to other ventures or fold entirely. The space economy grows slowly, driven by satellites and limited exploration, but never reaches the scale needed to make asteroid mining viable. Decades pass with little progress, and asteroid mining becomes a cautionary tale of over-promising and under-delivering. This pessimistic future is also possible, particularly if early missions are rushed or underfunded. A middle future sees incremental progress. Asteroid mining develops slowly, with occasional successes and frequent setbacks. By the 2050s, a handful of companies operate small-scale missions, supplying niche markets. Profitability remains elusive, but the industry survives on a mix of government contracts, research funding, and patient investors. Technology improves gradually, and each mission teaches lessons that inform the next. The space economy grows modestly, supporting limited asteroid mining without dramatic expansion. This plodding future lacks the excitement of a boom but avoids the despair of a bust. A fragmented future could emerge if international cooperation fails. Different nations and blocs pursue asteroid mining independently, with minimal coordination. Legal disputes over resources escalate, and competition becomes cutthroat. Some nations succeed while others are left behind, exacerbating global inequalities. Tensions over space resources contribute to broader geopolitical conflicts. In this scenario, the potential benefits of asteroid mining are diminished by mistrust and competition. A transformative future might arise from unexpected breakthroughs. Perhaps a new propulsion technology drastically reduces travel times and costs. Maybe advances in artificial intelligence enable fully autonomous mining operations far more capable than current systems. Or a discovery of extraordinarily rich asteroids, easily accessible and loaded with valuable materials, changes the economic calculus overnight. Such breakthroughs could accelerate timelines and open possibilities not currently imagined. History shows that technological surprises happen, and asteroid mining could be upended by one. A dystopian future, though unlikely, is worth considering. Asteroid mining could concentrate wealth and power in the hands of a few corporations or nations, worsening inequality and fueling unrest. Environmental damage from increased launch activity or debris creation could harm Earth's atmosphere and orbital environment. Militarization of space might escalate, with asteroid mining technologies repurposed for weapons or strategic dominance. Neglect of ethical and legal frameworks could lead to exploitation and conflict. Avoiding this future requires vigilance and intentional choices to prioritize equity, sustainability, and peace. A hybridized future might blend elements from several scenarios. Some companies succeed while others fail. Certain asteroids are mined intensively while others are protected. International cooperation prevails in some areas, but competition dominates others. The space economy grows unevenly, booming in some sectors and stagnating in others. This messy, complex future is perhaps most realistic, reflecting the unpredictability of human endeavors and the interplay of countless variables. Which future we get depends on decisions made today and in the coming years. Policy choices, investment priorities, technological developments, and international relations all play roles. No single actor controls the outcome, but each contributes. By thinking through these alternative futures, we can identify which paths to encourage and which to avoid. The future of asteroid mining is not fixed. It will be shaped by the actions and choices of many people over many years, and understanding the possibilities is the first step towards steering toward desirable outcomes. Part 17. The Long View. Stepping back from immediate challenges and near-term projections, we can consider asteroid mining from a longer historical perspective. What might future generations think of this endeavor? How does it fit into the arc of human development? Taking the long view offers context and reminds us that today's decisions have consequences that extend far beyond quarterly earnings or election cycles. Humanity has always been a species that explores and exploits its environment. From early migrations out of Africa to the colonization of remote islands, we have pushed into new territories, seeking resources and opportunity. The Industrial Revolution accelerated this pattern, harnessing fossil fuels and minerals to build modern civilization. Asteroid mining represents a continuation of this trajectory, extending human activity into the solar system. Whether this is celebrated as bold ambition or critiqued as insatiable expansion depends on perspective. Resource depletion on Earth is a real concern. Certain metals and minerals are becoming harder to extract economically as high-grade ores are exhausted. Recycling helps, but it cannot fully replace virgin materials in a growing economy. If asteroid mining can supplement terrestrial supplies, it could extend the lifespan of Earth's resources and reduce pressure on ecosystems. This pragmatic argument appeals to those who see asteroid mining as a necessity, not just an adventure. The timescale for asteroid mining's full maturation is likely measured in centuries, not decades. The first missions may occur soon, but building a robust, self-sustaining industry will take generations. Early efforts plant seeds, developing knowledge and capabilities that successors will build upon. Patience is required. Those investing today may not live to see full fruition, but their contributions lay groundwork for future prosperity. Technological evolution is unpredictable over long timescales. Technologies we consider cutting-edge today may seem primitive in 50 years. Conversely, anticipated breakthroughs may never materialize. Asteroid mining plans must remain flexible, adapting as technology changes. The long view counsels humility about predictions while encouraging steady progress toward goals. Cultural and philosophical shifts may alter how humanity views space and resources. Future societies might value preservation over extraction, choosing to leave asteroids untouched as cosmic heritage. Or they might embrace space development enthusiastically, viewing the solar system as humanity's birthright. These shifts depend on education, values, and evolving understanding of our place in the universe. The potential for asteroid mining to support life beyond Earth is perhaps its most profound implication. If humans are to establish permanent settlements on the Moon, Mars, or elsewhere, they will need local resources. Shipping everything from Earth is impractical. Asteroids offer materials to build habitats, grow food, and sustain life. In this sense, asteroid mining is not about enriching Earth but about enabling humanity to become multiplanetary. This vision motivates many in the field and gives their work a meaning beyond commerce. Existential risks, such as asteroid impacts or catastrophic events on Earth, add urgency to space development. A civilization confined to one planet is vulnerable. Spreading into space increases resilience. Asteroid mining contributes to this goal by making space more accessible and economically viable. The long view sees asteroid mining as insurance, a step toward ensuring humanity's survival. Ethical responsibility to future generations is a theme that resonates across cultures. What we do today affects options available to those who come after. Exhausting Earth's resources, polluting its environment, or failing to develop space capabilities could limit future possibilities. Conversely, wise stewardship and foresight can expand opportunities. Asteroid mining, pursued responsibly, could be a gift to future generations, providing resources and opening frontiers. The long view also acknowledges uncertainty and the limits of foresight. We cannot predict what challenges or opportunities future generations will face. The best we can do is act with integrity, pursue knowledge, and build capabilities that might prove useful. Asteroid mining fits this approach, developing skills and infrastructure with broad potential applications. In centuries to come, if asteroid mining succeeds, it may be seen as a turning point when humanity transitioned from a single planet species to a spacefaring civilization. The economic details we obsess over today may fade in significance, remembered only by historians. What will matter is whether we took the leap, whether we ventured into the unknown and learned to thrive there. The long view humbles and inspires, reminding us that we are part of a story much larger than ourselves. Asteroid mining is one chapter, and how we write it will influence chapters yet to come. Part 18. Comparing terrestrial and space mining. Understanding asteroid mining requires comparing it to terrestrial mining, the industry it might supplement or compete with. The differences are profound, but so are the similarities. Both seek valuable materials in challenging environments, Both require significant capital and expertise, and both face economic and environmental considerations. Examining the comparison illuminates what makes asteroid mining unique and where it borrows from established practices. Terrestrial mining begins with exploration, using geological surveys and drilling to locate ore bodies. Asteroid mining follows a similar pattern, using telescopes and spectroscopy to identify promising targets, followed by close-up inspection with spacecraft. Both involve uncertainty about what lies beneath the surface. A promising site might disappoint upon closer examination. The difference is that correcting mistakes in space takes years and costs far more than relocating a drill rig on Earth. Extraction methods diverge significantly due to gravity. On Earth, miners can use explosives, heavy machinery, and gravity itself to move material. Drills push into rock using weight, and/or falls into trucks or conveyor systems. In microgravity, these techniques fail. Equipment must anchor itself or use alternative methods like rotating screws to penetrate rock. Material does not fall. It must be actively collected. This fundamental difference means asteroid mining cannot simply adapt terrestrial equipment but must invent new approaches. Processing also differs. Terrestrial refineries use gravity-based separation, flotation, and chemical processes that rely on settling and flow. These methods work poorly or not at all in microgravity. Asteroid processing might use centrifuges to simulate gravity, magnetic separation for ferrous materials, or chemical processes adapted to weightlessness. Developing these techniques is one of asteroid mining's major technical challenges. Environmental impacts present contrasts. Terrestrial mining scars landscapes, produces tailings, and can contaminate water and soil. Asteroid mining has no ecosystems to damage, though it does contribute to launch emissions and space debris. The environmental case for asteroid mining rests on reducing Earth-based extraction, but this only works if asteroid resources actually substitute for terrestrial ones rather than simply adding to total consumption. Labor is another distinction. Terrestrial mines employ thousands of workers in dangerous, physically demanding jobs. Asteroid mining will be almost entirely robotic, at least initially. This reduces risk to human life but also means fewer direct employment opportunities. The jobs created by asteroid mining are in engineering, software, mission control, and data analysis, typically requiring advanced education. The social and economic implications differ markedly from traditional mining communities. Economics diverge sharply in scale and timeline. A terrestrial mine might cost hundreds of millions to develop and begin producing within a few years. An asteroid mining mission costs billions and takes a decade or more from conception to first returns. This extended timeline demands patient capital and tolerance for uncertainty that few industries require. The payoff structure is also different. Terrestrial mines produce steady revenue over years or decades. Asteroid missions might involve long periods with zero revenue followed by sudden returns if material is successfully brought back. Transportation costs favor asteroid mining in one specific scenario: supplying space-based markets. Lifting material from Earth's surface costs thousands of dollars per kilogram. Moving material within space, once it is already there, is relatively cheaper. An asteroid that delivers water to an orbital depot competes not against terrestrial water but against the cost of launching water from Earth. This niche advantage could make asteroid mining viable even when terrestrial alternatives are cheaper for Earth-based customers. Risk profiles differ. Terrestrial mining faces geological risks, commodity price fluctuations, and regulatory changes, but the environment is understood and technologies are proven. Asteroid mining adds technical risks inherent in space operations, longer timelines that increase market uncertainty, and legal ambiguities that terrestrial miners rarely face. The risk-adjusted return calculation must account for these additional uncertainties. Similarities exist too. Both industries require careful resource management, skilled workforces, and strategic planning. Both must navigate regulatory environments and environmental concerns. Both face boom and bust cycles driven by commodity prices and economic conditions. Lessons from terrestrial mining about project management, safety culture, and stakeholder engagement apply to asteroid mining. The industries are more connected than they first appear. The comparison suggests that asteroid mining will not wholly replace terrestrial mining but might complement it. Certain materials, especially those needed in space, could shift to asteroid sources. High-value, low-mass materials might justify the cost of return to Earth. Bulk materials like iron or silicates will likely remain terrestrial for Earth-based use, at least for the foreseeable future. The two industries will coexist, each serving markets where it holds advantages. Understanding this complementary relationship helps clarify the realistic economic niche for asteroid mining. Part 19. The next decade. Looking ahead to the next 10 years, what can we reasonably expect in asteroid mining? The timeline from today to the mid-2030s will likely see continued development, incremental progress, and perhaps a few milestone achievements. Setting realistic expectations helps avoid both excessive pessimism and unfounded hype. Technology demonstration missions are probable. Several companies and space agencies have announced plans to send small spacecraft to near-Earth asteroids to test extraction techniques. These missions will likely be modest in scale, perhaps extracting a few kilograms of material or demonstrating water processing on a small prototype system. Success would validate concepts and build confidence. Failure would provide data to improve subsequent attempts. Either way, these missions advance knowledge. Prospecting missions will continue. Identifying which asteroids are worth targeting requires detailed surveys. Missions that map asteroid surfaces, measure composition with spectrometers, and even core sample to understand internal structure will inform future mining plans. Some of these missions may be publicly funded scientific endeavors, while others could be commercial ventures seeking proprietary data. The line between science and commerce will blur as both communities pursue similar goals. Regulatory developments will unfold. International negotiations on space resource governance will continue, though consensus may remain elusive. Individual nations might pass additional laws or update existing ones. Industry groups could propose voluntary standards and best practices to fill gaps in formal regulation. Legal clarity will improve gradually, reducing uncertainty for investors even if comprehensive international frameworks remain incomplete. Investment patterns will evolve. Early-stage funding for asteroid mining startups may increase if technology demonstrations succeed, or it may contract if high-profile failures occur. Institutional investors and sovereign wealth funds might enter the space, bringing larger pools of capital but also demanding more rigorous business plans and accountability. Government grants and contracts will remain important, particularly for technology development and risk reduction. Partnerships and collaborations are likely to expand. Companies may team up to share costs and expertise. International partnerships could combine resources from multiple nations. Academic institutions, national labs, and private firms might collaborate on research and development. These partnerships spread risk and pool knowledge, making ambitious projects more feasible. Public engagement will grow. As missions launch and milestones are achieved, media coverage will increase. Documentaries, educational programs, and public outreach will raise awareness. Public opinion will shape political support, and companies that engage effectively with communities and stakeholders will build goodwill. Conversely, those that appear secretive or dismissive of concerns may face opposition. Incremental technical progress will accumulate. Advances in propulsion, robotics, autonomy, and materials science will make asteroid mining more feasible. These advances may come from asteroid mining programs directly or from related fields like lunar exploration or satellite servicing. Each improvement reduces cost or risk, bringing commercial viability closer. The space economy will continue expanding. More satellites will launch, space tourism will grow modestly, and lunar exploration will advance. This expansion creates potential customers for asteroid resources, particularly water for propellant. Demand remains small but rising, and by the end of the decade, a nascent market for space-based resources might exist. Setbacks are inevitable. Some missions will fail. Companies will run out of money. Technical challenges will prove harder than anticipated. These setbacks will test the resolve of investors, entrepreneurs, and policymakers. How the industry responds to failure, whether with resilience and learning or with retreat and recrimination, will shape its trajectory. Realistic expectations for the next decade involve steady but unglamorous progress. We are unlikely to see full-scale commercial mining operations or massive material returns to Earth. Instead, we will see technology proving itself in small increments, regulations slowly taking shape, and markets beginning to form. The foundation will be laid, the groundwork prepared, for the more ambitious activities that might follow in the decades beyond. Patience and persistence will characterize this period, as pioneers work through challenges that only become clear through doing. Part 20. Concluding Thoughts. Asteroid mining sits at the intersection of economics, technology, law, and human aspiration. It represents both opportunity and challenge, promising wealth and demanding sacrifice. Whether it succeeds depends on countless factors, from engineering breakthroughs to market conditions to political will. The journey from concept to reality is long, uncertain, and costly, yet many believe it is worth pursuing. The economic case for asteroid mining rests on specific conditions. Costs must fall, particularly for launch and operations. Technologies must mature, proving reliable and efficient. Markets must develop, either on Earth for high-value materials or in space for water and bulk resources. Legal frameworks must provide clarity and stability. These conditions are not guaranteed, but they are plausible. Each year brings progress, however incremental, toward making them reality. The broader significance of asteroid mining extends beyond profit. It represents humanity learning to use resources beyond Earth, a capability essential for long-term space exploration and settlement. It tests our ability to cooperate internationally on complex challenges. It raises questions about our values and priorities, forcing us to consider who benefits and who decides. These are not merely technical questions, but deeply human ones. Risks are real and substantial. Billions of dollars could be lost on failed missions. Environmental harm could result from increased launch activity. Legal disputes could escalate into conflicts. Inequality could worsen if benefits concentrate narrowly. Recognizing these risks and working to mitigate them is essential for responsible development. Opportunities are equally real. Asteroid resources could supply growing space industries, reducing costs and enabling ambitious missions. They could diversify Earth's resource base, relieving pressure on ecosystems and reducing geopolitical tensions over strategic materials. They could generate wealth that funds further exploration and development. They could inspire new generations to pursue science and engineering, building human capital for future challenges. The timeline ahead is long. The pioneers working today lay foundations that others will build upon for decades or centuries. Immediate profits are unlikely, but patient, sustained effort could yield transformative results. Success requires not just technological prowess but also wisdom in governance, equity in distribution, and care for both Earth and space environments. Asteroid mining is ultimately a bet on the future. It is a wager that space will become economically important, that technology will continue advancing, and that humanity will choose to extend its reach beyond one planet. The odds are uncertain, the path unclear, but the potential rewards justify the attempt. For those willing to accept risk and commit to the long haul, asteroid mining offers a chance to participate in something historically significant. As you drift towards sleep, consider the quiet ambition of this endeavor. Somewhere in the darkness beyond our world, ancient rocks drift in eternal orbit, holding materials that might one day build our future. The economics are complex, the challenge is daunting, but the possibility remains. Asteroid mining represents human curiosity and determination turned skyward, a patient reaching for resources and opportunity among the stars. Whether it becomes reality or remains a dream, the effort itself speaks to something essential in our nature: the drive to explore, to create, and to imagine possibilities beyond the horizon.